Let's talk about solving direct, direct square, and inverse variations. Answering problems that involve direct square, and inverse variations need very much focus on what type of values are being presented with. In this pre-break session, we are given with just one group of values, but we are going to solve for the unknown using a different scenarios. Number one, direct variation. Number two, inverse variation. And number three, direct square variation. So we have here the value y is equal to 16 is when x is equal to 2. Then what is y if x is equal to 4? And again, those said statements. Let us try to solve number one. Since all of these items here are under different scenarios, different types of variation, we have different ways to solve the value for the constant of proportionality, or we use k for that. So for number one, varies directly. Our equation is y is equal to kx. We are going to use the first pair of values to solve for the value of k, which is again the constant of proportionality. That value of k will be used later on to solve for the unknown in the next situation, in the continued situation. So first, let's substitute here the value 16 for y. You have k times 2, and then divide both sides by 2. The value for k, or our constant of proportionality, is equal to 8. This is the value that we are going to use to solve here for the value of y, because we are then asked to solve for y is equal to kx, because we are still on direct variation, and k is now 8 and x is 4. With the use of the constant of proportionality, the same value, our value for y, if x is equal to 4, becomes 32. Again, what happened here is we used the value for k to solve for the unknown. This is what happens to number one. But for number two, it's a different thing now. Do not say, I will use, sir, the same value for k to solve for number two. No, because in the first place, in number two, it's now a different type of variation, specifically inverse variation. So there is a chance that the value for our k is different. Let's try to solve it. So the mathematical equation for inverse variation is y is equal to k over x. Let's substitute the same given. You have 16 is equal to k over x, which is 2. Then we multiply both sides by 2. The value for k is now equal to 32. As you can see, the value for k for number one and number two are different because they are on different types of variation. Still, the value for k here is what we're going to apply to solve for the unknown. And it's stated there that y is equal to k over x, as we are sure that it's an inverse variation. And we are going to solve for y if x is equal to 4. So we have here y is equal to 32 over 4. So the value for y is equal to 8. So since again, the value for k are not the same for 1 and 2, that is also true when we go to number 3. And number 3 is concerned with direct square variation. So that the mathematical statement, or equation rather, for the direct square variation is y is equal to kx squared. Let's use the same given here. 16 is equal to k times x, which is 2, squared. This is actually 16 is equal to k times 4. Then we divide both sides by 4 to solve for k. The value left here for k is 16 over 4, or simply equal to 4. Again, as you have noticed, 4, 32, 8, they are of different values. We are then going to use this to solve for the next situation. Wherein we're going to solve for x if y if x is 4. So you have y is equal to kx squared. Let's solve for y. K is 4, solve here earlier. And then x is 4, then you're going to take its square. 4 squared is 16. So you have 4 times 16 here. So the value for y, for number 3, which is concerned on direct square variation, y is equal to 64. These are the different scenarios, even if we have the same values for the given, but the results are different because they are of on different variations, types of variation. This is for the previous session of lesson number 2. See ya.